you. Thank you so much for the introduction. I'm so excited to be here and share and share with you what I have been working on at CMU. So a bit about me. While I was trained as an architect, my work evolved over the past 10 years through combining design and computation to focus on interaction design. And I direct the Embodied Computations lab at CMU, as Lisan mentioned. And my research examines how designed interactions with computational technologies shape us and how we shape them. And my work aims not only to investigate novel interaction approaches, but also to elicit key design principles and frameworks that foster new forms of co-creations and communities of creative practice. At the same time, I seek novel ways to accommodate the growth and the variation of these interactions within larger systems and contexts. And the foundation of my research can be understood as investigating embodied human co-creation in creative practices and augmenting spatial experiences through extended reality, and advancing interaction design education in the realms of embodied and spatial experiences. And today I will focus a little bit on what part of the embodied computations part that I will talk about today. So we are entering a moment where the abstraction of human skills, capturing and modeling the ways we make, is no longer an end in itself, but rather the first step towards understanding how these skills can be sustained, adapted, and transmitted within emerging technologies and AI-mediated practices. In architecture and design, we have long worked to record and visualize the actions of making, whether in construction processes or in craft practices, but too often, the work stops at documentation and analysis, leaving the knowledge in visualization, videos, or data sets. For me, the central question is, what happens after we abstract and visually describe these skills? In other words, if we capture the making skills or processes of a ceramicist, what happens next? For example, I believe that one answer could be that AI and mixed reality will change how we learn, specifically hands-on making skills. So one answer to this question is that we can create a system to capture the skills from a human expert and use an AI-augmented extended reality tool to teach several students the same skill. If the next step is to build computational tools, drawing on large language models, machine learning, and extended reality, to transfer and scaffold this embodied tacit knowledge, then we must ask, what are the best approaches to do so? How might we design these systems to respect the contextual, the temporal, and tacit dimensions of skill? But I'm currently working on the instruction of these making actions instead of just abstracting them. Such are here, you can see an augmented reality point of view where the interface is guiding the person to move their hands in a certain direction to make. So we started experimenting with this approach and tested it by creating Origami Sensei. It's an AI-augmented mixed reality assistant that provides adaptive instructions for folding origami in real time. The system uses computer vision to detect what the person makes and suggests next steps. Then we went back to ceramics, and our research question was, what does the interplay between AI-augmented mixed reality systems and embodied craft practices reveal about the evolving roles of systems, learners, and practitioners? And to conduct this investigation, we adopted a research through design approach consisting of 3 phases of a formative study, a system design, and a user study. And this is included a studio ethnography and co-design sessions with ceramicists to generate design guidelines for the prototype and also iteratively develop it. An important point here that I will expand on later in my talk is, while we acknowledge the social aspects of learning a craft in the studio, the project is a probe of examining the interplay between the technologies, these technologies, and embodied craft learning. So we co-designed an AI-augmented mixed reality system that provides gesture holograms, adaptive instructions, and real-time shape feedback in physical space. It also has an LLM embedded or integrated into it, giving feedback to the learner or the practitioner. It had like 2 modes, one for learners and one for experienced practitioners, where it suggests forms for like experienced practitioners as a way of improvisation or like suggesting new forms to them while they are throwing on the wheel. So here I will show you like a video of the LLM interaction. I hope the sound works.
Check.
The clay becomes wobble. Rest your elbow on your leg to stabilize your arm. Then use the needle tool to shave off the uneven areas. With an even top, you can pull up again.
So here, like there is like a hologram overlay on the clay. It detects actually the shape of what the person is doing. And it's also giving feedback through the LLM with some instructions, but it also provides like video instructions to the learner. So we should be aware here that we can't encode all tacit skills and embodied skills in a system, but we can create interactions that help people develop these skills. And this is a very important point because, for example, the malleability of the clay depends on the humidity in the room, the moisture in the clay, and these are things that you cannot encode on how to react to them in the system itself. So one of the findings through the study was that the combination of more than one modality helped integrate contextual factors that the MR holograms or the XR holograms alone cannot provide, such as the feel of the clay, the amount of moisture that it should have. So beyond learning, as AI capabilities evolve, the system could evolve as a collaborator to open possibilities in professional production and creative practices. So going back to the research question of computational technologies, how they shape us and how we shape them, I focus on designing these computational tools to be more inclusive of people from different backgrounds and abilities. I look at craft because it has a lot of challenges and opportunities to help us shape how we design our interactions with AI, like multimodal AI and mixed reality. And one example of this craft is metalworking. The American Welding Society predicts that there is a deficit of 375,000 welders in the United States by year 2028. This means slower growth in our infrastructure, roads, bridges, and the construction industry as well. Training welders requires a lot of developing complex embodied knowledge, such as hand-eye coordination, movement, proprioception, and sound. And this is achieved through in situ apprenticeship and hands-on interactions with tools and materials. Along my colleague Dara Burl and a wonderful group of students, who some of them are here, we co-designed a mixed reality system to give students real-time feedback while learning how to weld. This is like a live welding. It's not a simulation. It actually has two modes, one for simulation and one for live welding. We integrated a MetaQuest 3 headset into the welding helmet that we designed. So it's like a modular helmet that could be 3D printed on a very small 3D printer that you could just have anywhere at home. We mainly wanted to create a system that enables instructors to teach more students and give them one-on-one instruction. So we created an AI augmented mixed reality system that helps students learn in real time and live. So here you can see that the student puts on the helmet, which has the MetaQuest 3 in it, and they start seeing the grid that they have to place on the table. And why they need to do that? Because like we come from different heights. So like specifying where your grid is or where there's your workspace is, it's different from every person. And just to give you an idea about live welding, if you don't have any experience about that, once you start welding, you can see the welding spark, but everything darkens. So you don't know what you're doing except like by seeing your weld, the spark. So you can't even see the welding torch that much. And this is how it looks like from the welding helmet without provided instructions, just the grid that the person put on the bench. And we had like just some dotted lines. And welding has like different parameters that you need to adjust and build skills on. Like if you see at the bottom, this is like a perfect weld line. It takes like hours and hours of training to achieve. But if you are too far from the welding bench while you are welding, you get dotted lines. If you are moving too fast, you also get dotted lines. If you are too close to the welding bench, it's like very wide line. So you need to build like these tacit skills of like achieving like the perfect line for the weld. So with MR instructions turned on, the student sees a ghost of their weld torch and instructions on how to adjust their hand motions while welding. For example, if you are welding too far from the welding bench, you are moving too slow or too fast. So you can also see that there are two hand angles that the student has to maintain, and we simplified the instructions and removed the verbal instructions later, but we need to record it. But for now, you can see that like if you are within the range, you are getting like more like inclusive colors and with green and like red, so it's more like you can detect what's the difference if you are out of range or inside of the range of the angles, speed, and distance. And in addition to giving like feedback to the student gets a summary of their performance, and they get to replay their welding and retry the lesson if they want. So it gives them like a score of what needs to be worked on, and they can replay each line they performed. Each student's live performance is also cast to the instructor's tablet. So they can also give them feedback and will be able to monitor more than one student. We customized the modular welding helmet that could be replicated on any small 3D printer, and it integrates the 3D Quest, the MetaQuest 3. We also integrated, like in the headset, other sensors in the welding helmet, such as sound and breathing sensors. And these were actually learned through the co-design workshops that I will explain in a bit. And we created an attachment that is attached to the welding torch, and this is how we measure the welding angles, speed, and distance. And it's just to clarify here, this is a system for novices learning how to weld. Applying it in the field and on site will require extra considerations regarding the worker's privacy and monitoring. And since the beginning of the project, we partnered with the Pittsburgh-based organization, the Industrial Arts Workshop, IAW, that annually teaches 100 teenagers craft-based metalworking in the historically underserved community or neighborhood of Hazelwood here in Pittsburgh. And my method to ensure that these designed interactions are inclusive and adaptive of people and their contexts is by applying a co-design approach that I call unmaking with. And I define unmaking here as a conscious method of deconstructing and iteratively remaking understandings, processes, and tools. And this approach encourages design researchers to integrate perceptual, social, and contextual considerations when designing interactions for computational tools in creative practices. We led a series of co-design workshops with the organization that included curriculum mapping, scenario development, and lo-fi experience prototyping. By involving partners in the on-site inquiry and development, their tacit knowledge and bodily lived experiences were embedded into valued design directions. We learned from them the importance of listening to the world, breathing exercises to manage the overwhelming experience, and the need to practice to develop muscle memory. So this is actually how we developed the UI with them. We brought like the headset. We had like a very early prototype. We asked everyone to try it, and then we asked them to like work on the UI. So we got like these acrylic sheets. We placed them on the welding booth with stickers and like markers, and we asked them to unmake what we created, draw, or add any instructions that they think it's important to have after they experience the prototype in the headsets. And the implications of this system, or these systems or developing them, include scaling up training the workforce. By adding a machine learning component to the system, it might also help to provide customizable and personalized feedback that fits diverse learning needs. So here, if you look at the diagram, I imagine that we can create a machine learning model based on the skills of the instructor and embed it in the headset that could be applied or used for teaching several students. And each headset gives personalized and customized instructions or feedback based on the student's performance. So through the workshops, we learned that experienced welders are able to assess welds through active listening. So you would be like just like welding in the booth, but then the instructor comes in and will tell you, oh, you are welding too fast, just by the sound. So we wouldn't have learned that if we weren't working closely with the welders community. So while we were learning, as I mentioned, the instructors would be commenting on that. And one instructor said, a good speed should sound like a sizzling bacon, not popcorn. So we built a machine learning model that distinguishes the sound in real time that are hard to tell apart by the ears of untrained welders, such as the sound of the wire speed is set too fast or the amperage is set to be too low. And we use tiny machine learning for this system. So we could add it to the system, to the headset, and once it detects the sound, it notifies the learner to slow down or to adjust the feed rate. And these are like especially the feed rate and amperage, they are very hard to detect by just like the headset, like you cannot see it from the torch. It's based on the sound that you detect. So this is a link of the project if you're interested in learning more about the project and as we develop it further. But Going back to the main question here is, how do designed interactions with computational technologies shape us, and how do we shape them? And I want today to show through the projects that this is like a bidirectional relation. While we shape these machines and the interactions while we are interacting with them, they also shape us. And in the projects I showed today, these tools could help us learn, but we also saw that through co-designing with practitioners, that it could help them reflect on their practices and externalize their embodied knowledge. So this is something like what we discovered about co-designing, that like it helps through using the tool itself. It helped the instructors to reflect on their skills, the design process itself, but also started talking about like what they teach in a different way as they externalize it and describe it. So here is like Mr. James at IAW reflecting on the prototype during one of the co-design workshops.
Either you did it or you didn't. Especially when I was welding around that curve, it was telling me things, you know, I've been a welder for 35 years, but it's still giving me feedback that would help me, because I've gotten into bad habits over the years, and I was coming around that bend, and I noticed I was like, well, I really am out on that bend, and I had to correct myself and hold it differently. So even as an experienced welder, just for 5 minutes of use, it's given me feedback and helped me. On the cover screen, I like that you've highlighted success. I like that it gives good and useful.
So here, like, we created like these acrylic sheets where they also like co-design the UI or refine the UI and the system. And we asked them to highlight what they like and how they can improve the experience through, during the workshop.
Either you did it.
Drawing on the unmaking with approach, we worked with practitioners not just to document their skills, but to deconstruct and reconfigure how those skills might be taught through computational systems. This co-design process revealed overlooked sensory channels, contextual variations, and culturally specific interpretations, elements often erased when skills are reduced to static abstractions. In both the ceramics and the welding projects, we began by abstracting and describing the actions of making, attempting to make some of the tacit knowledge explicit. But for me, abstraction of some of these embodied skills is only the first step. The real opportunity lies in what happens next. One answer could be how we design interactions that reintroduce these insights into practice, not as a rigid instruction, but as a guidance that adapts to different abilities, the context, time, and the unfolding nature of the act itself. This way, this was my talk today about embodied computations, and I'm happy to answer any questions. I mapped my talk today for like half an hour, but I'm happy also to play some of the videos of the ceramics project or other projects as well. And thank you so much.
Are those videos that you can put in the background?
Yes, yeah, then I can mute it actually.
Hello.
Okay.
Hello.
Happy to have.
Go ahead.
Yes. Yes.
Yes, so I have a two-part question. So for my first question, I see that for both the clay sculpting and for the welding project, both of them very fascinating projects. I actually was wondering, typically with these kind of environments, the issue that I tend to have with interacting with these environments is due to the fact that it is very visually dependent paradigms, and there is not a lot of sensory feedback. Mostly when you're using, for example, the sculpting one, there is no true feeling of sense of depth perception to the same extent that you have just looking at the sculpting with your own eyes through the VR headset. Was there ever a consideration for either of these programs to try to approach different sensory modalities in terms of like interaction with the environment, so there's like sensory or physical feedback to prevent the user from pushing past a point that might ruin the interaction with the clay, or let's say if potentially the user is using the sculpting gun and they go to a point where it might start harming or damaging themselves or things surrounding them. I believe that physical feedback would be a logical step here, and I was just wondering in what sense has that been considered, and if that's a future implementation to further refine the current version.
So for the welding project, it was actually initially what we had in mind is the haptic feedback in the glove and including it. But through the workshops and through the training, you realize that this is not an important aspect because you are getting feedback from the live welding of the torch itself and the push. For the simulation mode, we had like integrated sound as like feedback while you are welding. You hear the sound changes. So even if you are too far in your bedroom from while you are welding with the torch, you still sense or learn about the sound changing as you weld. This is actually, you came with your own perceptions or plans, and this is what you're gonna do. And then when you go into the site and working with people in the field, you realize that, okay, this is not an important aspect. But then like you realize that sound makes a huge difference in the experience, which is something that I didn't have in mind when I was starting the project. Another aspect of also like for diverse skills and abilities, we realized, or it came up from the sessions with the instructors, that they saw that this is a very helpful tool for the hearing impaired. Because while the hearing person is welding, they cannot tell from the sound of the weld that they need to adjust something. And then they cannot hear the instructors, and they need to have like an interpreter, like a sign language interpreter between the instructor and the student. So what came up from these workshops is like that you could use this tool for training people who also like we didn't put into considerations when we started. And some of the workshops came up was saying, or the insights that came up was instructors wanted to point out about at a certain point and a certain action while the student is doing it, or just to show them how it's done. But it was so difficult to be on like with this first point of view person and telling them this is how to be done. So that was also like an insight that we learned. For the clay project, I believe that it's very hard to integrate haptic feedback on the fingers, because it's actually you build this knowledge or embodied knowledge through interacting with the material, and I believe that like you need the direct interaction with the material. So that's why we chose the visual overlay and the sound modality, and it's again, like these headsets and technologies, they are very limited. Like I see Lusan now is wearing the Ray-Ban glasses, and I'm like, oh, I just wish it has like an overlay. But yes. And so, so back to this point, these tools now have these limitations of low resolution, for example. But the idea is like you don't need like a lot of overlay and separation between the material and the interaction of what you're making. You still want to keep that interaction, but like how can you develop, or like, again, like the ceramics project was more about like, if we have this probe, how can we understand the role of these technologies and its implications in learning an embodied skill? So we weren't like seeking a perfect application to teach you every step of ceramics. We were more like, okay, what are the implications? And what are the implications for someone who doesn't know how to wheel through? And then another person who's like very experienced, how this could help in improvising while you are making. And this has other implications in design, even in architecture, in sculpture, how like these AI augmented tools and even extended reality tools help you or collaborate with you to improvise while you are designing and making. I think that answered your question.
Dina?
So I have a somewhat general question for you. Given your success with potters and with welders, what are your thoughts about moving it into other areas where there's such a critical need, like, say, healthcare? Now, I'm thinking of registered nurses who practice on oranges, giving a shot, for example, or physicians doing a lumbar puncture on a mannequin. It seems to me it would have some real possibilities.
So would you mind maybe just like paraphrasing the question?
So about how we can apply these tools in other domains, such as medical training and nurses and nursing training as well. Is that how I? Do you have any adjustments to that question? I mean, is that the right question? Like, if I understood it correctly? Yeah. Okay. So yes. I think like this system has its implications, and it will be useful for medical training because it decreases the risk of training. We haven't considered going into this direction because it has a lot of, it needs a lot of approvals in terms of applying it. And also I'm interested more into the creative practices, more like craft, more like making. Other domains that we considered was also even dancing and choreography, because it has like the body coordination as well. There has been some work, a lot of work in extended reality and surgeries. And this is because of the high risk and of like practicing on real patients. I wanted to add another thing, sorry. Sorry, I lost my thought. Yeah, I will remember. Sorry.
So I understand that your tool is focusing on training, right? But when you are trying to control all the movements and register as data by a computer, sometimes like one of the most strongest power of human condition is the intuition of our movements. Mm-hmm. So with this kind of technology, you don't think the human condition is in a risk, and we're started to learn as a machines instead as a humans?
So the question is about losing human intuition when we use these systems and becoming machines.
Yeah, exactly, because like, for example, like in craft, you know, like it's very important. It's also another layer that is politician and is cultural. For example, you cannot do this with craftsmen because they are so dread about using technology. They felt like replace it by technology. Maybe in the US you don't have too much like craftsman culture, but I'm from Mexico, and there it's super important that we have to respect it because it's part of our cultural heritage and it's intangible. How do you think this kind of technology, because technology we cannot stop it, but how this technology can have a conversation with the human condition?
Yeah, in the work we are doing, we are mainly like saying that this is like to augment the training. So especially that like there are a lot of dying crafts, and the way of looking at it, like you have a lot of, for example, ceramicists in, for example, across the globe who are dying, but they have like these very unique artisanal styles. So the implication of the work is not just like to transform people into machines, but there is like the part of like archiving these skills and how we can learn from them. Like if I can learn from a ceramicist who's 100 years old, then it's something that I would value. In the practical applications here, there are actually like a lot of, as I showed the statistics, there are dying most of the welders are baby boomers and they are retiring right now. And there is like a huge gap that like you cannot cover. There are also other considerations in the trade that affect it. It's not just training. But for example, one of the things that came up is that this is like a great recruitment tool to young generations who can practice over and over and try the skill before deciding that this is like a job that they want to do. So there are other, like in my work, I don't want to replace human skill. I actually want to preserve human skill. And my question is like, okay, we have been documenting making grammars and like descriptions and like all these videos, but then like what do we do afterwards? And these projects are one of the like an answer or one of the answers to that question. But for example, like with Kim here, we are working on like how can you interact with an archive of skills or of embodied skills. So this is like could be another answer to that question. Like if we have like these skills documented in a way, how can we create new interactions to interact with them?
Or creating new craft, or like that's something interesting. And I think like just to add into your project, because I think your project is awesome. Like you have to go to Mexico, by the way, and there you will find a lot of like craftsmen. But the point that the craftsmen are disappearing is because also there is another layer that we have to take in consideration, that is the economical layer. They have very low salaries. And the young generation, because I was in Oaxaca one day and I saw like this textile craftsman and a little chair next to the textile, and I asked, what's the little chair? And the lady told me, it's for my nephew, but my nephew don't want to weave any time because they prefer to be in social media. Mm-hmm. Why you don't digitalize my textile? And this is something really interesting because they really are looking forward to this, but the problem is how we can support them economically. Mm-hmm. And maybe they can make more money saving their data, and in in the future someone else can use it. I think it's something that maybe it's interesting in your project.
So when we started the whole investigation, like this is like maybe 5 years ago, we started by looking at ceramics and craft, but as a first case study, and we started getting like the comment of like why, like you don't need ceramics, like everyone is doing ceramics, like we don't need to preserve it, but actually you have masters of craft that you can. With welding, it was very easy to justify the system, the application, and the investigation. And not just because of that, it's because also that there is like a helmet integrated in the whole thing, so it makes sense that you are wearing a headset. But mainly I didn't want to have like a perfect working system. I was more interested in how can we answer these questions and what are the implications. I was very curious about that. And even with welding, what I learned are that there are other considerations, even social considerations into recruiting welders in general. So there is, of course, there is the gender issue, but there are also other issues that I learned from working with the instructors as well. And I remember now it was about the Formula One. So there has been research about Formula drivers training so many times on in simulators versus drivers who have been driving in real time in life.
Generation drivers.
Well, it's also cheaper.
Yes.
I have a nephew who's a pilot, and he could not afford all the flying lessons, but he could afford the simulators, and you can get licensed that way as well.
So actually, when they did the study, the ones who did the simulators and the training with all the games, they actually were better than the drivers. So that's part of like replying to your question regarding surgery and medical training.
I think, yeah, in the case of the woman who's asking about the medical.
Oh, no, sorry.
I think that was I think the way her question was also directed was at the sort of targeted kind of simplicity of, and I totally understand not being able to get into the medical arena just for the logistics of planning alone, but like of practicing injections or drawing blood by puncturing an orange, you know? And I think the kind of applications in the trade school arena or area is super, super interesting. And having experience with ceramics, I'm surprised you even went into ceramics because the variables of like clay density and softness, there's a spinning wheel, is it spinning in the correct rotation? Is it spinning quickly enough? Because it isn't in all of those videos, right? And like, oh no, you have to have it centered. There's just so many variables. And with welding, like primarily, we're trying to get a straight, clean weld. And you know, just thinking about other sort of trade school applications as we are entering that kind of space where, yeah, trade learning is just not as popular as it once was. When you think about sewing and fabrication, you know, textile fabrications, which are also generally linear, right? And that kind of linear application of perfecting a kind of small but clean goal, as opposed to the sort of many, many, many variables involved in the ceramics, seems like such a great way to also bring awareness, visibility, access to a kind of trade learning through a VR experience, and then also be able to kind of enroll in a program and get the one-on-one experience. Like, I think there's just so much opportunity in this sort of trade realm. It's really beautiful.
Yeah, thank you. And also I wanted to add like another angle from like this work is like everyone is trying to race to encode human knowledge in AI and train as data sets to train a machine learning model to use it for generative AI. But we haven't looked at like embodied skill and what it means to build AI models that has a generation like that we could build Gen AI on it. So I don't want to encode like the skill into a system, but I'm curious about like if we are looking at like creative writing and how we are training models on creative writing, what it looks like if you are training a system on sculpting or ceramics. So this is like more like an investigation. It's not like I want to take the human and put them in a machine as was mentioned here, but it's more about like what can we do? Like how if it's going to be done, what are the implications and what cannot be done? And my claim is like there are a lot of felt experience that you cannot encode in these systems, but you can create interactions to help people build these skills.
Carmen.
While you were, so thanks for the presentation. You've shown a wide range of applications for these embodied experiences with technology. Well, one of the terminologies that I was wishing you'd talk about was this spatial knowledge that you have to build into these platforms in order to understand space. Because you show us that the headsets have an inbuilt software that understand the hand movement, can read them. So I just want to hear your statement about what is in this work that you show us the spatial knowledge that you.
Are you talking about the spatial knowledge of the human or the system? The system. In the ceramics, we actually used a camera to detect the silhouette of what the maker or the ceramicist is doing and building the form in the system. So there was a camera on the side that I didn't show the system diagram for. And this is like how it triangulates the space where the person is interacting with the holograms and the physical form. For the welding project, for example, it was we like in live welding, the systems we starting seeing that there are some imperfections or some inaccuracies of like 2 or 3 millimeters of detection. And these are the limitations of the headset. But it's actually, what I didn't show is we have like the second controller of the system is the calibration. So we have it on the table, it has like a station on it. And while you are welding, there's the headset, the torch controller, and a controller attached to the table. And putting the grid and saying this is the grid that I will be working on in the beginning, it defines the space that the system is looking at. And in Origami Sensei, like the folding, we had like the projection on the table, and the camera on the desk, like directed towards the desk to detect the light square of where you are working. I don't know if that's like what you are mentioning, but there were like some spatial insights that came up from the ceramics project because it had like the 3D aspect of manipulating the material from different angles and how like the system is basically predicting where your hand is compared to like some occlusions and
what about because I saw some of the instructions were actually quite detailed. So what about things like the water content?
So that was like point of the contextual factors, and it was supplied, and that's something that we were saying that like you can never do that unless you add more sensors and you make it like a machine of like detecting humidity in the air and like maybe measuring the moisture in clay. But we realized that the video that plays like tutorials on the side while you are working, you could ask the LLM to play a video for the step, and that gave the person a sense of what the texture should look like. Because again, this is a felt experience that you develop over time. It's not something that you can detect easily.
I think what's kind of really interesting is I see these sort of like training wheels, right? Because like they're kind of introductory things that are meant to guide someone into a craft. And so I wonder what the experience of these learners once you take the training wheels off. You know, like once, because, you know, for example, like certain tutorials with things like this, you can kind of follow how much do we fixate on the overlay versus actually what's happening, what we're feeling, and once that overlay disappears, how do they kind of recalibrate that?
Yes. So this is like the futures work section in any paper I put, is the long-term learning part, like how like what you learn, like especially like on Origami Sensei, what we did is like we tested it against learning from a video tutorial. And of course, like what we found is the feedback helped the person learn and perform or finish the task faster, but then the question is like, who remembers the action on a long run, like in next month or 2 months from now? And we are currently working on that in the welding projects, and we are wondering about that, but this is a very expensive and a time-consuming user study that if you know any sources for funding, let me know. But currently what we are doing is we are doing a user study of you train in the lab for a few times based on some papers in cognitive science and embodied training. You need like certain numbers of lines to train, and this is how you learn the motor skill, like for 11 times, for example. So this is what we are trying now, like just like a 1 hour session, which actually needs 1 other hour of session. So 2 hours training per person to study the effect of learning and measuring this. And I come from a design and computation background, and I didn't anticipate that even measuring this needs a lot of debugging and technical skills and a lot of technical trials and debugging. And I'm actually learning that part as well.
Oh, all right, one last question, I think we have time for.
Thank you for sharing the projects. Both of the two projects are very inspiring. They're very task-oriented. So my question is, what if the user make really bad decisions or actions and they ruin the project? Does the tool ever ask the users to give up?
Or actually, also, will the LLM actually make really bad suggestions?
I like the idea of the LLM being mischievous. I would like that. That would be another project. They actually, like in the ceramics project, they did like mistakes, and they got the feedback that they are doing the mistake, and they were able to repeat the action. And that's one of the findings that we also did through the studies, that they appreciated that they could go back, redo the clay, and learn that again and again and practice by themselves compared to asking the instructor to give them feedback. That was usually we had in the user studies, watching a video or just a qualitative user study of how their impressions about the system, and that was one of the winning. Usually it's not. There were parts where they saying I feel like this part is too mechanical, and I had to improvise, and this is when the mistakes happen. And this is we talk about that these systems need to be more customizable and more adaptive to the person, because they start to improvise in a direction that it needs to have more scenarios of what could happen and or how you could train it for different scenarios. And this is something a finding that you could put as a future work for if you are building a Gen AI for embodied skills. They need to be able to train on different failing scenarios in this embodied skill and how they can give feedback. I hope that answers your question.
Thank you.
Thank you.